So hello all, I am starting the recording right now. So welcome to the NPTEL Week 9 Digital Circuits ee147. This course is offered by Professor Shantanu Chattopadhyay from IIT Kharagpur. Myself, I am Shubham. I am pursuing PhD in Department of Electrical Engineering from IIT Gandhinagar. Okay, so let's start today's questions. So which one of the following is a sequential access memory? Okay, so you have a couple of minutes to think and answer the question. So these are pretty simple questions. Let's discuss the answer. So we have different types of memory devices. These are not memory devices, these are storage devices, okay? Like magnetic disk, CD, and DVD. These are storage devices, okay? Your RAM is memory device. So in all of this, you can directly provide address and get the data, okay? So what is the meaning of sequential access memory? Sequential access. It means that suppose I have an array like this. So in order to get the access of data at location 3, I will have to go through 0, 1, 2, and 3. Okay, so this is quite separate from the conventional memory we discussed these days. So these days, what we do is that we directly provide the address to the decoder. Address is provided to the decoder, and decoder directly selects the data. Okay, so 1 second. Mm, okay, so in these days, what memory does is that you will have a decoder. Fine. So you will get input, suppose 0, 0, 1. So it registers it as 1. So what it will do is that it will activate this line, and the data present in this line will be sent, okay, as the output. So this is non-sequential access. In sequential access, what will happen is that in order to get 1, you will have to get 0, and then you will get the 1. Okay. So in case of magnetic disk, you can provide address. In CD and DVD, you can provide access. You can provide address. In RAM, you can also provide address. So actually, the question is misleading. The correct answer is magnetic tape. So in magnetic tape, you have to sequentially go through all the data till you reach the desired address location. Okay, so this is the answer. Fine. So the next question is, SRAM stores the binary information in A, the form of electric charges in capacitor, B, internal latches, C, lookup tables, D, the form of electric charges on the inductor. So you have to keep in mind that the data that is stored in form of charges, especially in the volatile memory, does not last for a long time. Okay, it will eventually, the charge will dissipate through leakage and your data will be lost. So for a reliable memory that is fast enough, you might have to have a better way of storing it instead of charges. So I will discuss the solution now. So this is your SRAM. This is back-to-back connected inverter. Okay. So what happens here is that these are gates. So suppose you have stored a data one over here. Okay. So this one will pass through this inverter and zero will be stored over here, and this zero will pass through the inverter and one will be stored over here. Okay. So this zero actually keeps this as one, and this one keeps this as zero. So this is a continuous feedback system, right? So that's why the data is stable. Okay. So this is basically a configuration of your SRAM. This is a very simple SRAM, which is also known as 6 transistor SRAM, because it is made up of 6 transistors. So these are, each inverter has 2 transistors, PMOS and NMOS. So in total there are 4 over here, and there are access gates, which are made up of NMOS. Okay. So the SRAM stores the binary information. So even though you can see that there is 1 and 0, these are complementary in nature. Suppose if you want to store 0, then it will be 0 and 1. You cannot store two different data at the same time. So this stores 1 bit data. Now the question is, stores binary information in the form of, so definitely it stores in the form of internal latches, right? So this is the latch configuration. For lookup tables, you will need flops, right? I think I'm mistaken. In case of lookup tables, you would need, if you make it in terms of lookup tables, it will be basically a flop design. Okay, it won't be SRAM. If the data, if the data is stored in the form of electric charges, then that is the case of a DRAM. Okay, so in DRAM, it looks like there is an access gate and there is a huge capacitor. Okay, so whatever data is there, it is stored as a charge of the capacitor. If the charge is high, then it is 1. If it is low, this is 0. Okay. So the next question: which of the following statement is false? SRAM memories have shorter read and write compared to DRAM. DRAM memories have shorter read and write compared to SRAM. SRAM memories occupy minimum area compared to DRAM memories. DRAM memories occupy minimum area compared to SRAM memories. So the only hint that I can give here is that the speed of the memory is dependent upon the current that it can produce when it is turned on, right? So the data that is present inside the memory is reflected at the output depending upon the current. If the output has a capacitor, right? So the memory has to either charge it or discharge it depending upon the content that is stored in the memory. Okay. So you would need a strong driver inside the memory to drive the load. The load is your output. So greater the current, faster it will charge up or discharge, and faster will be your read and write. So in order to have a high current, the most reliable design is a logic gate design, which has a pull up or pull down network. In case of, in another situation where we have um, data stored in the form of charges, the data will also be then reflected in the output, but it will uh, take a lot of time. I think this much hint is enough. You can proceed now. I will give you a few minutes, then I will discuss the solution. and the size of the memory is dependent on the number of transistors it has. More the number of transistors, bigger the memory is, and technically you would say more expensive it is. So let's discuss the solution. Your SRAM looks something like this: back-to-back inverter connected. Okay. Suppose this is your load. Okay. You switched on this transistor. This is on. This is the load, and it has a capacitor over here. Okay. So the data in the capacitor will determine what data is stored inside the memory. Okay. So this is the memory location. Now this is equivalent to this circuit. Okay. So now suppose the gate is 1. Okay. If Q is 1, so what will happen? If Q bar is 1, what will happen? The data 0 will be stored over here because this NMOS will be on. Okay. So when this gate is on, what will happen? The whatever charge you have stored over here, it will find a path to discharge through this NMOS. So this NMOS is basically acting as a driver. Okay. So this has driving ability. There is current, there is high current. So more the current, less time, it is faster. In case of DRAM, it is something like this. There is an access gate transistor, you have a huge capacitor, and you have a small capacitor over here. Okay. So now when this transistor is on, suppose suppose VDD is stored over here. Okay. And it has some charge, it has some capacitance CD, and this is the output capacitance, output load. So suppose it is discharged to 0. So finally the charge will be CL plus CD into V equal to CD VDD, or CL equal to, or V equal to CD CL plus CD VDD. So what you observe over here is that the final output voltage is not equal to VDD, even though stored was VDD. So first of all, the data that is stored here is not completely reflected in your output. And the second thing is that it has no driving ability. So here it is following the principle of charge sharing. Eventually, the time it will take is dependent upon E minus T by RC, where C is the combined capacitance. Okay, and R is the resistance of the NMOS transistor over here. So this takes exponential time for the complete charge sharing to happen. Whereas in this case, it has a fixed time. Okay, so DRAM are usually slower as compared to SRAM. Now, what other thing is that SRAM memories occupy minimum area as compared to DRAM. So this is not true because your because SRAM has 6 transistors, whereas your DRAM has 1 transistor, and the size of your um, memory is dependent upon the number of transistors it is made up of. Okay, so so uh, relatively SRAM takes about 6 times more size compared to DRAM. Okay, so that's why this statement is incorrect. SRAM memories occupy minimum area. Okay, DRAM memories occupy minimum area compared to SRAM memories. This is correct. DRAM memories have shorter read write compared to SRAM. Uh, yes, no, this is wrong, and this one is correct. So answer is B and C. Okay, so B and C. So moving on to the next question. So what is the ROM size? Read-only memory size when it has 16-bit data lines as input and 8-bit data lines as output. Okay. So this is a simple mathematics question where 16-bit data address lines means that with each unique combination you can access a particular unique location. Okay. So the hint I would like to give is that the number of unique locations is the total number of defined addresses, and if you multiply with the size of that location, you will get the size of the memory. Okay. So this is a pretty straightforward question. Okay. It will not take much time. I think everyone should give it a try. I think sufficient time has been provided. Okay. So in this case, 16-bit address line, which means that suppose this is my number. So this location is different from this location. So the total number of locations is possible at the total number of states that are possible, which is 2 power 16, and the size of the each location is 8 bits. So this is your answer. Okay, which is 2 power 19. So this is 2 power 19 bits or 2 power 16 bytes. So 2 power 10 bytes into 2 power 6. Okay, so this is known as kilobyte. Okay, so KB 2 power 6 is basically 64. So this is a 64 KB memory. Okay, so one can also ask, suppose what is the size of the address bits if my memory size is suppose 16 GB. Okay, and it stores one word of data. This is a doable question, right? So let's look at the solution. So has anyone got the answer? So right now I will say that there is 16 GB of data, okay, and one word of data is stored in each location. So now one word is consisting of 32 bits, okay. 16 GB data, it's about 16 into 2 power 10 megabytes, which is 16 into 2 power 10 into 2 power 10 kilobytes, which is 16 into 2 power 10 into 2 power 10 into 2 power 10 bytes, which can be 8 bits, okay. So now this is your total memory size, which is equal to size, data size into 2 power address. So 2 power address is 2 power 4 into 2 power 30 into 2 power 3 divided by data size, which is 32 bits, which is 2 power 5. So this is 2 power 4 plus 30 plus 3 minus 5, which is 2 power. I think it got disconnected. So I hope the screen is visible again. So the answer is 2 power 4. So address bits are 42. Okay. So the next question is, which of the following statement is true? Hamming code can correct and detect only single bit errors. Hamming code can correct and detect up to 2-bit errors. Hamming code can correct and detect up to 3 bits and 4 bits. let's discuss the solution. Okay. So Hamming code can correct and detect only single bit errors. Okay. So that's the answer. So in Hamming code, what happens is that in locations 1, 2, 4, 8, which are actually the power of 2, like 2 power 0, 2 power 1, 2 square, 2 cube. In all those locations, you put extra bits which are which we get by XORing other bits. Okay. So when we XOR, we have the ability to get only one bit. We have the ability to recover only one bit when there is an error, and the location of that one bit which contains the error is given by your uh, extra bits, which is your Hamming code. Okay. So we will see that in the following question. So a 12-bit Hamming code is given. It contains 8-bit data and 4-bit Hamming code. What was the original 8-bit data word stored if 12-bit Hamming code is this? So as I mentioned earlier, the position of Hamming code is in the power of 2s. So you can basically identify which is the Hamming code. You have to separate that Hamming code from the 12-bit Hamming code that is given and provide the 8-bit original data. Okay. Let's discuss answer. Okay. So 0 0 1 1 1 0 1 1 1 1 1 0. So location of a parity bits are 0 1. Location of parity bits are 0 1. It's not 0 1. Actually, there is a error in numbering. It starts with 1 2 3 4 5 6 7 8 9 10 11 12. Okay. Positions are 1 2 4 and 8. So if you remove them, you are getting 1 1 0 1 1 1 0 1 1 1 1 0. So this is your answer. So these parity bits 0 0, and at 4 you have 1, and at 8 you have 1. So this you get at 1 you get by XORing numbers at 3, then 5, then 7, then 9. Okay. 7, 9, and I have one. There is one more number. 11. At 2, you get by XORing 3, 4 you cannot include because 4 is already occupied by a parity bit. So this comes from here, this position. 3, 4, 5, 6, 7, 8, 9, 10, 12. So 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1. I think I made a mistake. It should be 1, 0, 1, 1. It should be 1, 1, 0, 0. So in this case, 3, 5, 7, 11. Now you have 3, 6, 7, 10, 11. Okay. 3, 6, 7, 10, 11. This position you will get by doing 5, 6, 7, 12. 5, 6, 7, 12. This position you will get by 9, 10, 11, 12. 9, 10, 11, 12. Okay. So let's verify. This should be XOR of. This should be XOR of 3, 5, 7, 9, 11. This should be XOR of 3, 6, 7, 10, 11. This should be XOR of 5, 6, 7, 12. This should be XOR of 9, 10, 11, 12. So this is correct. This should be 0. This should be 0. And this should actually be 1. So moving on to the next question. Find the 12-bit having code for the given 8-bit data. So I will explain the Hamming code here. Okay. So in this case, 1, 2, 4, 8, these are the positions where your extra Hamming code will be present, right? Now remaining data you place starting from 3. So in red, I have put 3, 5, 6, 7, 9, 10, 11, 12, 8 places, 8-bit data, right? And for C0, C1, C2, C3, we have the value that you get after joining these positions. Okay, fine. So these positions that you get is basically from. So this is the trick: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, as per the rule of the uh, Hamming code, for 8-bit data, you need only 12-bit Hamming code. Okay, so any data beyond 12, we won't consider. Now, for 1 to 12, we have 0, 0, 0, 1, 0, 0, 1, 0. So in order to get C0 position, you have to XOR, right? So since this is C0, that is 2 power 0, 1, 2, 4, 8. So when it is 1, you have to consider the first position. Okay. So this is since at this position we are already filling the parity, so we will consider the rest of the positions. So 3, 5, 7, 9, and 11. Now in case of C1, so C1 is basically 2. So we will this is 1, 2, 4, 8. So we have to check in all those places where this data, where this all those positions corresponding to 2, where it is where the data is 1. Okay, so corresponding to position 2, the data is 1 in. So we won't consider this because 2 at this position we will fill the Hamming code, right? So 3, 6, 7, 10, and 11. Okay, so that is how you get for 2. For 4, you have to consider all the bits at the position corresponding to this 4. So here we have, so since we are having the Hamming code over here, so we want to consider this place, then 5, 6, 7, and 12. Okay, so that's how you get 5, 6, 7, and 12. So that is the solution. So what is the size of the Hamming code for a 10-bit data word? Okay, so hint is that if you're, so it's something like if you have a R-bit data, R-bit Hamming code, so it should be 2 power R minus 1 should be less than K plus R, where K is the data, R is the Hamming length. Okay, so I think you should be able to solve this using this hint. So if you have 4-bit parity, it should be able to tell the location of the error in the range from 0 to 2 power R minus 1, right? So because if you have encoded any data in the form of Hamming code, then if you face any error during the transmission, the Hamming code will tell you the position of the error. Okay, so right now, so the data should always be less than 2 power R minus 1 minus R. So in this case, what will happen? K is equal to 10. So 10 plus R less than 2 power R minus 1, or 11 should be less than 2 power R minus R. Okay, so take R equal to 4, it will be 2 power 4 minus 4, which is 16 minus 4, which is 12. So that goes to, therefore r equal to 4, k equal to 10. So the total size will be k plus r, which will be 14. Okay. So B is the answer. Moving on to the next question. Programmable array logic contains AND array and OR array. You have to answer if it is fixed and programmable. So these are pretty much straightforward questions. You have to basically memorize it. Programmable array logic basically contains of, answer is C, programmable and and fixed OR. So it will look something like this. All your signals with their complements. So this will pass through a OR gate. This will be your output. Okay. So in whatever location you want to make a connection, what will happen is that you will establish the connection like this. Okay. So those connection will pass through the OR gate. So this is your PL logic. Fine. The next question is programmable read-only memory contains. So the answer is B. So anyways, you cannot do both fixed and, because if both are fixed, then it would not be programmable at all. So at least one of it should be fixed. Second thing is that if both of them are programmable, then it will unnecessarily add to the complexity of the programming. Okay. So one has to be programmable, and another has to be fixed. So this will look something like, So these are all possible combinations. This will go through and get and this will go through the OR gate. Okay. So the condition, the program that you, so the lines that you select, okay, that you program will be reflected in the output. So this is your EPROM. This is your programmable PROM. This is your PROM. So moving on to the next question, which of the following memory technology is not programmable? So the correct answer is A, fuse. Okay. So once the fuse has been established, it is not possible to change it. The next question is, which of the following memory technology is volatile in nature? So volatile memory is the one that stores the information as long as the power supply is provided. As you remove the power supply, uh, it will lose its operation. Okay, it will lose its memory. So the correct answer is C, SRAM. So SRAM is basically your back-to-back inverter connected. So the inverters can retain the information as long as the VDD and the ground voltage is supplied to it. Okay, as soon as you remove the VDD ground connection, the data will be lost. Okay, so answer is C. The next question is, which of the following outputs of the following circuit? I will give you 5 minutes to do this problem. So let's discuss the solution. So at this point, this is your A, this is your B bar, A, this is your C, this is here you have B, B, and here you have C and C bar. So at this location you have AB bar, this location you have AC, at this location you have AC as well. Here you have BC and here you have BC bar. So now after you perform the OR, it should be C A plus B, and here at this node you have 0, at this node you have AB bar plus BC bar plus AC. Okay. Oh, I missed A bar over here. So it should be A bar BC. So A bar BC. So it is AB bar plus AC plus A bar BC bar, which we can write as A So F1, 1 second. I think I will have to add page. So F1 is basically XOR of 1 A B bar plus C, XOR of 1 in A can be written as 1 A bar plus 0 into A, which is A bar. So it can be written as XOR of A bar B bar plus C, which will be A bar B bar plus C whole bar plus A B bar plus C. Which will be A bar B bar plus A bar C plus A B C bar. Or I can write it like this way. AB bar plus AC plus AB bar whole bar. Okay. So this is your option A. XOR of 0 and A is 0 into A bar plus 1 into A, which is basically your A. So F2 is basically AC plus BC. So your answer is option A. Moving on to the next question. For the following given circuit, identify the outputs A and B. So let's discuss the solution. We have so it will be xy plus xz bar. D will be xz bar plus xy bar plus yz. So that is your option D. Okay. So this is the last question I had. So that's all for today's tutorial. If you have any doubts, you can let me know. Okay. So that's all. Bye bye. Thank you for your time. I'm stopping the recording right